Okay, good morning, everyone. Today we'll look at first order filters from chapter 6. As mentioned on Monday, chapter 6 will be assessed on quiz number 8 next week on Monday. And it will not be assessed on the final exam. Okay, so chapter 6 will not be part of the final exam. Speaking of which, if you haven't taken a look at it yet, you should click on the link from the front page which says final exam. It will take you to this page, and I state it in big bold letters at the top. Please read everything on this page. Okay. I went over some of these points on the first day of class, and of course, this is part of the syllabus. Several students did read this in the first week of class, and as well as submitted the form that is at the end of this page. I'll quickly hit the main points. Final exam, if you didn't already know, counts for 20% of your overall grade. So it's a big chunk, but it's not significant to, if you don't do well on the final, it's not going to sink your grade. And so I believe 20% is a good balance between, not too much and not too little. It is mandatory. It is not optional. Mandatory is in the sense that you can choose not to take the final, but I do not drop it, right? If you choose not to take the final, if you're happy with your grade as it is, with the rest of the 80%, plus all the extra credit points that I have in the homework, a student could potentially end up with like an 83 or 84% in the class, even without the final. Okay. So if you're happy with your B and you do not wish to take the final, that is up to you. Okay. So mandatory is only in the sense that I would not drop the grade from the final. You would just get a 0 from there. But again, if you're at an 83 or 84% before the finals and you're happy with your grade, you can simply walk away without taking the final. Then there are some rules on there. There are some options. And again, read through everything and then contact me, reach out to me if you have any questions. The final exam schedule, as most students are aware or should be aware, that is set by the Cal Poly administration. It is not up to faculty. It is standard for every class, across every department in every college across the entire university. There are 2 links here. You can look up your final exam schedule for your other classes also from these links. As with regards to this class, our final is on a Friday. It's basically the last Friday of the term at 10 o'clock in the morning. It's not 10 p.m. I need to change that. Okay. It's at 10 o'clock in the morning on that Friday. That is the university scheduled date and time. Okay. You have the option of taking it earlier. Okay. Every student has that option. You can take it with the finals with the other 2 sections, which is on a Wednesday at 7 a.m. and 10 a.m. Okay, that is off finals week. That's the alternate times. So if you wish to get done early and leave town, you can do so on Wednesday. There is also an even earlier option, which is on the Saturday before finals week, or the Saturday after the last day of class, which is not going to be in this room. It will be in the EE building. I have not yet reserved the room. Most likely it will be room number 126 and 130, depending on the number of students I have. And that will be on the Saturday after the last day of classes, which is March 15th. Last day of class is Friday, March 15th. So the Saturday final is March 16th. Again, this is completely optional. Okay. This is an option that many students take. And I need to know how many students would like to take it on a Saturday or at an alternate time. Okay. And so for that purpose, I have a form that is at the end of this page, at the bottom of this page. Several students actually submitted this form in the first week of class itself, like 9 weeks ago. So if you haven't already taken a look at this, go ahead and read this page, read everything on this page, determine what your options are, and submit this form at least by Wednesday of next week, right? Wednesday of next week is basically, I'll be busy with lab finals all week long. I'll have to grade finals. So I'll be busy on every single day of next week. Well, I'm busy every single day of every quarter anyway. But again, next week would be especially busy because I'll be grading lab finals for about 75 students. So all of my days will be packed. I need to know by at least Wednesday how many students are going to take the final on that Saturday. I need to reserve the room. I need to print out the finals. I need to know how many students so that I know how many seats I need. So again, you have a week to figure it out. The earlier, the better. All right. And as there are topics that are listed on here, there's information about the equation sheet, all of the rules, everything. So again, please, please, please read everything on this page and reach out to me if you have any questions. All right. Okay, so that's enough about the final exams and the options. Let's go to our topic for today. And that should be 04. All right, so we stop right here. Today, we are going to look at filters, more specifically first order filters based on inductors and capacitors. Based on inductors and capacitors. So inductors and capacitors have impedance. That impedance depends on the frequency, right? For a capacitor, it is ZC equals 1 over J 2 pi F times C, meaning ZC is inversely proportional to the input frequency F. ZL, on the other hand, is J omega L or J 2 pi FL. So it's J 2 pi F times L. It is directly proportional to the frequency. So I came up with a handy dandy table, or as I like to call it, a handy dandy table that allows me to quickly analyze any circuit containing inductors and capacitors for the filter behavior. Okay. ZC is inversely proportional to frequency, meaning at extremely low frequencies, when F or omega tends towards 0, low frequencies, capacitor behaves like an open circuit, right? ZC, if F tends towards 0, then ZC would tend towards infinity, infinite impedance, which is, if you remember from chapter 3, if you apply a DC voltage to a capacitor, once it reaches full charge, capacitor behaves like an open circuit. Current cannot flow through anymore, right? There's no more charge imbalance, and so electrons stop flowing. Effectively, current stops flowing in the circuit. Capacitor behaves like an open circuit. Tied back to chapter 5, ZC is inversely proportional to frequency. So tending towards 0 basically describes DC behavior. Okay. DC behavior. At the same time, if frequency increases, or as F tends towards infinity, ZC tends towards 0. Impedance of a capacitor would be very, very low. It would be equal to 0. And the capacitor behaves like a short circuit, or as I like to call it, SC. Open circuit OC and SC. An inductor, of course, is the exact opposite. So at low frequencies, when F tends towards 0, inductor behaves like a short circuit. And at high frequencies, it behaves like an open circuit. SC and OC. You can have this table on your equation sheets to quickly analyze any filter circuit containing inductors and capacitors. Okay, call this my handy dandy table. Okay. Also at this point, I'd like to remind omega is 2 pi F. Right? F is the time domain expression, and omega is the describes the angular frequency. One full circle is 360 degrees or 2 pi radians, hence 2 pi F. Okay, so based on this behavior, we can construct 4 different circuits from inductors and capacitors. Similar to chapter 4, if you have a capacitor in a circuit, along with the other resistors, you have a RC circuit or RC filter. If you have an inductor, it is a RL filter. And it's a cross matrix. You can construct both kinds of filters using both kinds of components. You can construct a low pass and a high pass filter using both RC as well as RL circuits. And we'll look at what each of these terms mean, what each of these circuits would mean, and how they would work. Okay. The low pass or the high pass refers to the frequencies. Okay, so the low and the high it refers to frequency values of the incoming signal. Low pass meaning the low frequencies are allowed to pass through. High pass means the high frequencies are allowed to pass through. Okay. And if you have both kinds in the same circuit, then it's a band pass filter, or it could be a band stop or band reject filter. Okay. So if you have both low pass and high pass in the same circuit, you would create a band of frequencies that are allowed to pass through, or a band of frequencies that are blocked. So you would get a band pass filter. Most filters that we use in everyday life would be band pass filters. Graphic equalizers on your boombox or your audio systems, they are band pass filters. They pass a certain band of frequencies. Satellite phones, satellite communications, mobile communications, television, radio, all of those permit a certain band of frequencies to pass through. Everything else is blocked. So most of them are band pass filters. Okay. And other times we have low pass and high pass filters. Now, low and high is relative. Okay, it depends on the application. If we talk about human hearing, right, the audible range of frequencies, standard definition is 20 hertz to 20 kilohertz, right? But most people, like me, would not be able to hear anything above 15 or 16 kilohertz. Okay, hearing is not that good anymore. In my youth, we listened to a lot of loud music and movies, and now we pay the price when we age nearly 50, right? So always stuck earphone and a headphone in your ear. Yeah, we don't realize it until until decades later. Anyway, so low and high is relative. What is considered low or high for a normal human hearing would be nothing when it comes to electronic communications. So something like a frequency of 15 kilohertz would be considered as a high frequency when we talk about human hearing, whether music, movies, vocals, doesn't really matter. But when you compare it to, let's say, like a wireless router signal, wireless router operates in the gigahertz range, which is 2.4 gigahertz and 5 gigahertz, right? Gigahertz and kilohertz. So compared to a wireless router that operates in the gigahertz range, a kilohertz frequency would be low frequency. So it's relative. So the same 15 kilohertz frequency would be considered as high for audio applications, human hearing, whereas for a wireless router, it would be like low or a mid frequency. So low or high is relative, right? Low or high is relative. Since we're using one energy storage device, if it's a RC filter or a RL filter, it is known as a first order filter. If you have two components, two energy storage devices, then it's a second order filter. If you have more than two, then it's like third, fourth, fifth, sixth, higher order filters. Filters by itself, even for EE majors, is a specialized topic. It's an entire course. Actually, there are multiple courses you can take for filters and filter design. Okay, so it's a very big, expansive topic by itself. So even EE major students would not study higher order filters unless they take a higher level course. Let's look at the first one of these. It's a RC low pass filter. Okay, RC low pass filter. Excuse me. What is the first thing we notice about this? We have a resistor and a capacitor in the circuit, hence RC, of course. V out is taken across that capacitor, meaning V out is equal to VC. Voltage across the capacitor is the output voltage, right? Excuse me. But what do we see here? The resistor and the capacitor are connected only at this one single node. There is no other component connected to that node right at the top. We are simply taking the output at that node. So what does it mean for the connection between the resistor and the capacitor? They are in series, right? They are in series. So I could draw the circuit like this. Okay, you have V in, and you're taking the output across the capacitor. All the standard rules still apply. Passive reference configuration, current flows from the power supply. It's a series circuit. And so the current I is the same through the resistor as well as through that capacitor. That doesn't change. Okay. Point of entry is plus, point of exit is minus. And so exactly the same polarity, from the passive reference configuration. Here's where it gets interesting. If you take the output across the capacitor, it works as a low pass filter. You know this because I've already stated right at the top. It's a low pass filter. But if you take the output across the resistor, it works as a high pass filter. That's the cumulative effect of the capacitor energy storage. Okay, I'll let that sink in. Take a 10-second pause. Let me know if you have any questions. All right. Any questions at all? Yes.
Find what a low pass and high pass filter, what is that? Like, does it only filters like voltages at high frequency?
Yes. I'll explain through everything. We'll go through everything. Okay. So the first thing we'll do is we'll do a quick analysis using that handy dandy table. So I will model the behavior of my capacitor at low frequencies first. At F equals 0, or as F tends towards 0, meaning low frequencies, the capacitor behaves like an open circuit. If you need any help remembering this, 0 and O, and capacitor C, so OC. The capacitor behaves like an open circuit at 0 or low frequencies. So if it behaves like an open circuit and I redraw my circuit to reflect that, what is my V out? Without knowing anything about the circuit, without knowing any parameters, component values, capacitor behaves like open circuit at F is equal to 0. I'm applying a voltage. Since this is open, it's equal to Vn. There is no current flowing to the circuit, meaning the resistor does not have any voltage across it. Vn is transferred directly to the output. That's the cumulative effect. And so V out would be equal to Vn. So as F tends to, again, this is the quick analysis. Then we'll look at the equations and quantitative description also. But this is the quick and easy analysis. So as F tends towards 0, capacitor behaves like an open circuit. If it behaves like an open circuit, V out would be equal to V in. So if you apply multiple input signals, doesn't matter the voltage, but if you apply all these signals in here into the circuit with frequencies at the low range, it'll all pass through to the output. You'll obtain a voltage at the output. But when F tends towards infinity, capacitor behaves exactly the opposite. It becomes like a short circuit. If it behaves like a short circuit, then what is my output? Both points are connected to each other. If both points are connected to each other, is there any difference in potential? So voltage is equal to 0. So V out goes to 0. Hence, the effect of the capacitor, is making it seem as if the output frequency, not output frequency, the output voltage goes to 0. So effectively, when you put this together, it is working as a low pass filter, meaning all of the input signals that have lower frequencies are allowed to pass to the output. Anything with higher frequencies, the output voltage goes to 0. So they are being blocked. Does that make sense? Hence, it works as a low pass filter. Okay, so this is the quick and easy analysis using the table, using the handy dandy table. You can analyze any filter circuit using this table. Okay. All right, so then let's look at the mathematical equation. Now, you won't go, I won't do every step of this derivation, but I will show you how it would work. Remember that these are all phasors, right? So I current would be equal to V in over ZEQ. V in over ZEQ means R plus ZC. ZC is, this is simply from Ohm's law, right? The total current in the circuit I equals V equals I times ZEQ. So I equals V in over ZEQ. So this simply becomes R plus 1 over J 2 pi FC. Then V out is across the capacitor VC. And so V out is equal to VC, meaning I times ZC. We would plug the value of I directly from there. You plug the value of I, then you insert the equation for ZC in there. You have V out on the left, you have V in on the right. You translate V in on the other side, meaning you bring it back to the left, you obtain an expression in terms of V out over V in, which is nothing but our transfer function h of f, and that is given by the expression h of f is 1 over 1 plus jf over fb. This is the expression that we would obtain, where f is the variable. F is the variable. It notes the values of the incoming input signals to this filter circuit. It could take on any value. FB is a constant, and that constant is determined directly from the values of R and C. 1 over 2 pi RC. FB, the B stands for break frequency. Break frequency, FB. Okay. Again, the derivation is rather simple or not simple, but straightforward. You have a circuit comprising of a series connection of a resistor and a capacitor. You apply a voltage V in. Voltage V in could be any input, could have millions of different values for frequencies, doesn't really matter. But it's V in. V in applied to R plus ZC. That's the total equivalent impedance, ZEQ. So from Ohm's law, you can write the value of the total current flowing to that circuit. I would be equal to V in divided by ZEQ. It's R plus ZC. You plug that value into Ohm's law again. So V out across the capacitor is I times ZC. You have V out on the left, V in on the right. You bring V in on the other side of the expression, you obtain V out over V in. V out over V in is a transfer function H of F, which describes the behavior of the circuit in terms of the variable frequency. FB is a constant. It is given by 1 over 2 pi RC, depends on the values of the resistor and the capacitor. The B stands for break. It's basically the demarcation line between the pass and the block bands. It is also noted as FC. Okay. FB is also noted as FC. And the C stands for cut off frequency. Cutoff frequency. More often than not, you would see FC rather than FB. Since the book and the online homework system uses B, I'll use B in the class. Okay, but if you come across FC, it means exactly the same thing. Okay, cutoff frequency or FB. And we'll talk a little bit more about FB in just a minute. One other point I'd like to make is if you take a different class with a different professor, they might be using a different book. And most books might use omega C. Okay, omega C would simply be 1 over RC. Omega is 2 pi F. So F is equal to omega over 2 pi. And so it's the exact same equation, except you either multiply or divide by 2 pi. All right, questions before I go into the explanation for FB. Any questions? Okay, so FB, the break frequency, notes the line between the pass band and the block band. If I was to plot V out as a function of frequency F, I would obtain, let's see, at 0 hertz for a low pass filter, my output voltage should be equal to V in, right? The maximum value. As the frequency increases, meaning 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hertz, I would still expect V out to have a value equal to the V in input voltage. After a certain point, that point would be FB, that voltage should drop to 0 volts. Okay, 0 volts. So for a low pass filter, what it means is that all frequencies below FB would be allowed to pass through to the output. All frequency signals above it would be blocked, where V out would go to 0. So FB is the demarcation line between the pass band and the block band. All frequencies below FB would be allowed to pass through to the output because V out would be equal to V in. All frequencies above FB or beyond FB will have a value of equal to 0 volts. Does that answer your questions?
But why is the curve not like continuous?
So it would be continuous, yes. So this is for an ideal. So excellent question. This is for an ideal filter, but real life never works like an ideal filter, right? And so it would be a gentle slope. The slope would look like this. This is a plot of the magnitude of the transfer function h of f. We would think that an ideal filter would have a sharp cutoff, which is never the case, right? You would never get that kind of cutoff. And so this is more of an approximation of what a real life filter would look like. We have a gentle slope going all the way down towards 0. This is a magnitude of the transfer function normalized to 1. Okay, normalized to 1. You can have multiple plots. You can have V out versus as a function of frequency. You can have h of f as a function of frequency, right? In both cases, the plots would be similar. The low frequencies would have high value, higher frequencies would have lower value. And because h of f is a complex quantity, it has magnitude and it has phase. The phase is affected, as seen here in this image, in this figure, goes from 0 towards minus 90. 0 towards minus 90. When f is equal to fb, the transfer function simply becomes 1 over 1 plus j. 1 over 1 plus j. When f, the variable f, the incoming input signal is exactly equal to fb, it becomes 1 over 1 plus j. When you solve it and find the magnitude of 1 over 1 plus j, you get or you obtain a value that is equal to 0.707. 0.707. Okay. The output voltage drops to 70% of the input voltage at the cutoff frequency. So until you reach the cutoff frequency or the break frequency, the output voltage is at V in, V in, V in, V in. And then once it's slowly dropping, of course, it reaches 70% at cutoff frequency. And that point is taken as the dividing line between being allowed to pass and between being considered as blocked. Even after the cutoff frequencies, the output voltage is still, it's not 0. You still obtain some output, right? You still obtain some output. It's not, again, it's not ideal. It's not going all the way to 0. You still obtain some output, but we consider that to be blocked by the filter. Okay. It's the demarcation line where the power of the circuit, of the output power, drops to 50% of the input power. Okay. So output power drops to 50%. P out would be equal to 50% or 0.5 of P in. Power, input power. Power is V square over R. When you solve that equation, you get 70 or 0.707 in terms of voltage. Hence 0.707. Okay, let's take a 10-second pause. Let me know if you have any questions. I'm going to bring up this circuit diagram right here. So if you have any questions, feel free to ask. Any questions at all? Okay, well, then let's look at the other flip side of, not flip side, but the other side of the circuit, which is if you take the output across the resistor. As I told you, right, we get a high pass filter. So again, if you do a quick and easy analysis at F equals to 0, we saw the capacitor is open circuit. Capacitor is open circuit, V out is equal to 0 volts. Nothing is across the resistor, right? No current being flown. No current flows through the resistor. At F equals infinity, capacitor behaves like a short circuit. And if it behaves like a short circuit, output across the resistor is equal to the input. V out would be equal to V in. All right, let's take a 10-second pause. Think over that. Let me know if you have any questions. Does that make sense? Right? Exact same circuit. There's no difference whatsoever. I didn't realize this until the year after I first took this class as a student, that they are the exact same circuits. Right? They are in series. So resistor and capacitor in series. It's just that we are changing where we are taking the output. Okay. And this is the reason why, well, not this is the reason, but in cheaper or inexpensive speakers, especially the small ones, if they are two-way speakers, there is a woofer, small woofer, and there's a small tweeter in there, right? The cube speakers, the ones that look very cute and do not take up a lot of space, the ones that come in a home theater in a box system. And I kid you not, I have seen speakers where you simply have a resistor and a capacitor, and the connection point, one end of each component is just twisted together to form the top node, and the other two ends are directly mounted on top of the the tweeter and the small woofer. So it costs less than, like, I don't know, not even like a buck or less, $2 probably. Less than $2, you'd have your filter. It probably doesn't even cost that much. Like, resistors are so cheap or inexpensive, they cost like cents. Like a whole bag of resistors would not cost you more than a few dollars. So it's a very quick and easy way to make a filter. And since you have both high pass and low pass in the same, in the same circuit, all you got to do is you take your resistor and a capacitor output. This would go to, because it's low pass, the base of the woofer, and this would go into the small tweeter. Even car audio speakers, they would have like a woofer and then a small tweeter mounted on top of it, and they would also use something similar to this. In really inexpensive ones, they would simply have a resistor capacitor mounted or soldered directly on top of the speaker itself. Something like this in the classroom, I would expect, it would be like a higher quality. So it'll probably have an actual circuit board with actual, with high quality capacitors and inductors in there. Professional audio systems, the big speaker boxes, the good ones will have like a big circuit crossover network with like heavy inductors with coils, better filtering, and better filtering with better current control capacity. So the point is, you can have a high pass and a low pass filter circuit directly in the same circuit, the same series connection of resistor and a capacitor, right? Take the output across the capacitor, you have a low pass filter, you take the output across the inductor, across the resistor, it's a high pass filter. The derivation for the voltage remains the same. It's a series connection, so it's I is equal to V over ZEQ. You translate that into V out over V in, and you obtain this expression. The denominator is exactly the same. There's an extra component in the numerator, JF over FB. And this is a transfer function that describes the high pass behavior of the exact same circuit. Okay, so it's JF over FB divided by 1 plus JF over FB. The FB remains exactly the same. For a RC circuit, it is 1 over 2 pi RC. which makes sense, right? It's the exact same circuit. There's no difference. We are simply changing where we are taking the output from. And so the transfer function of that filtering of the filter is different. But the break frequency is going to remain the same because the component values are exactly the same. That would not change. If you graph this or you plot this, it looks different. Right? This is your pass band. This is the block band. Okay. This is the block band. On the right is the pass, on the left is the block. And because an inductor works exactly the opposite of a capacitor, if you take the voltage and apply to an RL circuit, you'll get the exact opposite filters. For a RL circuit, if you take the output across the inductor, you would get a high pass filter. Okay, and if you take the output across the resistor, you would get a low pass filter, which is right here. Okay, again, the analysis and the workings remain exactly the same. So at F equals 0, inductor behaves like a short circuit. Inductor is a short for DC. F equal to 0 is DC. So if it's a short circuit, my input is available at the output. Hence, it is allowing low frequencies to pass through. Hence, a low pass filter. If frequency increases towards infinity, inductor behaves like an open circuit. If it's open, nothing reaches the output. High frequencies are blocked. Effectively effectively behaving as a low pass filter. Again, this is a quick and easy analysis using the handy dandy table. Okay, this is the quick and easy analysis. You simply model the circuit. You model the component behavior as a open or a short. Replace that component with a open circuit or a short circuit, and then just simply analyze it very quickly and efficiently. So at low frequencies, the voltage is blocked. The voltage is allowed to go to the output, and at high frequencies, it is blocked. So it's a low pass filter. Make sense? Right? And then again, it's the exact same circuit. If you analyze this here, at F equals 0, inductor is a short circuit. Output goes to 0. So V out is equal to 0 volts at low frequencies. At high frequencies, when F tends towards infinity, inductor behaves like an open circuit, meaning my output is equal to the input. V out is equal to V in, and hence the behavior of the circuit is as a high pass filter. Okay, again, it's the exact same circuit. Inductor in series with a resistor, so it's a RL circuit, but depending on where you take the output from, you obtain a filtering behavior, and that filtering behavior could be either low or high, depending on where you're taking the output. Okay, it's the exact same circuit, no difference. The equations also remain exactly the same. It doesn't matter if it's made out of RL or RC. If it is a high pass filter, it has the exact same transfer function. If it is made out of RL, the FB remains the same. FB is R over 2 pi L. And you see it exactly the same in a RL low pass. The low pass RL has the same transfer function as a RC low pass. No difference whatsoever. Okay. So low pass filters have the same transfer function. Doesn't matter whether they are made out of capacitors or inductors. And the break frequencies, which of course depend on the component values, are the same for RC and for RL. So it's a RC filter, doesn't matter if it's low or high. It has the same break frequency equation. And if it's RL, it's the same break frequency equation. Okay. All right, questions. Questions about anything. Anything at all. Obviously, it's a lot of information to take in, so please review it. Okay, reach out to me if you have any questions. 2 slides after this, there's a summary of the magnitude and the phase equations for both low pass as well as high pass. Okay, it is simply the direct equations to calculate the magnitudes and the phase angle. Remember, it's a complex quantity. It's a complex quantity. H of f, transfer function, is a complex quantity. So it has both magnitude and phase. So if you think of it as a vector, it forms a right angle triangle. Right? Right angle triangle. So to find the magnitude, does that make sense? When you solve the equation for the transfer function to find the magnitude and to find the phase, you can use these equations because they would form the sides of a right angle triangle, and the angle, the phase, of course, is the angle that it makes with the x-axis. Okay. Again, you do not have to memorize any of these equations, right? They're there. You should know how to use them. There is a problem right here, and we do not have time to get into it, you know, in class. So I'm going to post a video that describes the solution, and the slides will be updated in the class notebook. Okay. This is basically similar to the example we solved on Monday. On Monday's example, we were given the graphical description of the transfer function of a network. And then we were given a input voltage with 3 components that was applied to this network. And we were just, you know, we were asked to find the output. So it's the exact same here, except here the transfer function is not given to us. But the circuit diagram along with the components is given. So what we would do is we would first analyze this using the quick and easy table. We perform the analysis, determine what kind of filter this is. And we already just talked about it. So we know that if you take the output across a capacitor, it should be a low pass filter, right? But again, I will go through each and every step, and I will post this online on the website shortly in a few hours. All right. But example on Monday was a graphical description of the transfer function. Here is the analytical description, I mean the equation from the transfer function, and then the procedure is exactly the same. All right. So we'll end class here today. You let me know if you have any questions, and I will see you all on Friday. Oh, get started on the homework. Okay, the homework I believe is due on a Friday right now. Okay, and then Friday's material will be due on Sunday night. So take a look at the homeworks. And if you have any questions, I'm here.